Let us work a few questions of the finite state machine. So it is possible to name any sequence circuit as a finite state machine. We are naming as a finite state machine based on as and when we are using the flip-flops. If at all we are using two flip-flops. By using two flip-flops, there are 4 possible combinations. Each possible combination on these two flip-flops becomes a state. So as and when we are using some flip-flops, the number of states in that circuit will be a finite number of states. So out of finite number of states, out of, say for example, using two flip-flops, if at all we are talking, out of 4 states, for circuit purpose, we may be using sometimes all the 4 states, or may be using sometimes only 3 states, sometimes maybe possible even 2 states. Anyway, so out of so many available states, the circuit is going to use finite number of states. Based on this, we are naming a finite state machine. So let us look at a problem here. It is mentioned a clocked sequential circuit has 3 states A, B and C and one input X. As long as the input X is 0, the circuit alternates between the state A and B. As and when X is 0, the circuit is switching between the state A and B. Okay, next if we continue the question, if the input X becomes 1, as and when the input X becomes 1, either the circuit may be in the state A or in state B, irrespective of the state A or B. As and when the X becomes 1, the circuit goes to state C. So as and when X becomes 1, when the circuit is in the state A or in B, it is switching to the state C and remains in state C as long as X continues to be 1. The circuit returns to state A if the input becomes 0. So whenever the circuit is in state C, it is coming to state A if at all the input X is 0. As long as X is 1, it is in the same state C, but as and when X is 0, the circuit is switching from state C to A, and from then on it repeats its behavior. So once it is coming to state A, it is going to repeat as usual, similar to the beginning. Assume that the state assignments are A equal to 0, 0, B equal to 0, 1 and C equal to 1, 0. So first bit in this question is draw the state diagram of the circuit. Next one is give the state table for the circuit. The third one is draw the circuit using D flip-flops. So it is a question. So we are looking based on the description. There are 3 states. State names it is mentioned in the problem as A, B and C. These are the 3 states in the circuit. Whenever the circuit is in the state A or whenever the circuit is in the state B, the circuit, if at all in state A, if at all it is getting input X is 0, it is coming to B state. As and when X is 0, it is coming to the state B. But when the circuit is in the A state, if at all X is 1, if the input X becomes 1, if the X becomes 1, whether it may be the state A or B, the circuit is going to state C. So that if at all it is getting 1, X as a 1, it is switching to state C. Similarly, when the circuit is in the B state, if X is 0, it is coming to state A, but if at all X is 1, it is coming to state C. When the circuit is in state C, as long as X continues to be 1, it is in the same state. The circuit goes to the state C and remains in state C. It remains in state C as long as X continues to be 1. So as long as X is 1, it is in the same state. But as and when X becomes 0, it is coming to state A. And then onwards it will repeat. So whenever it is coming to A, as usual, if at all x is 0, it is coming to B. If at all x is 1, it is coming to C, and so on. So this is the answer. It is the answer to the A bit. It is the answer to the first bit. It is a state diagram of this finite state machine. Then the next thing we are looking as give the state table for the circuit. So if you come to the B, whatever the description we are looking in the state diagram, this description is to be formatted as a table. That formatted table we are naming as state table. So in the state diagram, if at all we are looking at the description what we are looking is what is the present state of the circuit as and when x input is 1 or as and when x input is 0, the circuit is switching to which state. So this information we are reading in the state diagram. So what is the information we are having the state diagram, that if at all we are formatting as a table, the table we supposed to name as state table. So that we are looking the description with the present and next state, the state diagram, the description we are looking always the present and next state. Based on this, if at all we are coming to state table, the column headings will be the present state. So the present state possible may be any one of this, maybe A, maybe B, maybe C. And coming to the next state, so next state will differ based on x. If at all x is 1, it is something else. If at all x is 0, it is something else. So when present state of the circuit say A, if x is 0, if at all x is 0, it is coming to B state. It is coming to B state. But if at all x is 1, it is coming to state C. Similarly, when the circuit is in the state B, if x is 0, it is coming to A state. But if at all x is 1, it is coming to C state. As and when the circuit is in the C state, if x is 0, it is coming to A state. But if at all x is 1, it is in the remain same state, C. So that it is the answer to the B bit. So this we are naming as state table. This we are naming as state table. The next bit we are looking, draw the circuit using D flip-flops. Okay. So from these A and B bits, what we are able to understand is, once we know for the given circuit state diagram, for the state diagram we can build the state table. Or for the given circuit, if at all we know the state table, while knowing the state table, it is possible to build state diagram. And coming to this C bit now, we are looking here, there are 3 states in the circuit. In this finite state machine, there are 3 states. So what we are looking is, say for example, the circuit is presently in state B. If x is 0, it is coming to A state. If x is 1, it is coming to C state. Okay. Similarly, we are looking, if at all circuit is in C state, if x is 1, it is remain same state. If at all x is 0, it is coming to A state. So what we are looking is, we are having here 3 states. Based on the present input, the circuit is switching. Say for example, the B state with x is 0, it is coming to A. With x is 1, it is coming to state C. So that based on x value, where it has to switch, that is to be remembered by the circuit. If at all it is to be remembered by the circuit, then definitely the state information is to be stored in the flip-flops. Then only it is possible by the circuit to where to switch. We are looking here, there are 3 states. To distinguish these 3 states, we are in need of 2 binary variables. So each binary variable is to be stored in one flip-flop. So that to store 2 variables, we are in need of 2 flip-flops. And it is mentioned, the state assignment. A is mentioned to assign with a 0, 0. B is mentioned with assignment 0 1, with C is mentioned with assignment 1 0. It is a thing which is given. So out of 4 combinations on the 2 flip-flops, we are having the usage in this circuit only 3 states. We are having the usage of only 3 combination. One combination 1 1 is not used by the circuit. So this part of the work we are naming as state assignment. After state assignment, we have to realize circuit by using D flip-flops, so that the state table data we need to format as in the binary form. Instead of names ABC, we used to name these states with the binary notation. So with this binary notation, we need to format the state table. So if you do that, present state. So present state information is in 2 flip-flops. So one flip-flop output Q1, other flip-flop output is Q0, and come to the next state. Next state with X is 0, next state with X is 1. So next state information also are looking in these 2 flip-flops. So wherever we are having A, it is to be replaced with 0 0. Wherever we are having B, it is to be replaced with 0 1. Wherever we are having C, it is to be replaced with 1 0. So B, if X is 0, it is coming to A state. With X is 1, it is coming to C state. When it is a C state, with X is 0, it is coming to state A. With X is 1, it is remain the same state. So this we are naming state transition table. So this state table data, when we are looking in the binary format based on the state assignment, this we are naming as state transition table. We are naming as state transition table. So we are looking basically the solution of the C bit. So based on this description we are looking, we know here what is the present state and what is the expected next state based on the X on each and every flip-flop. Knowing the present state and knowing the expected next state based on the X value, we need to bother what inputs we need to apply. We need to bother what inputs we need to apply on each flip-flop. So what inputs we need to apply on each flip-flop, this information we can read while looking to the excitation table of the flip-flop which we want to use. In this question it is mentioned we want to implement the circuit by using D flip-flops, so that by knowing the D flip-flop excitation table, it is possible to fill. The D flip-flop excitation table we know. Zero to 0 transfer D0, 0 to 1 1, 1 to 0 0, 1 to 1 1. So what we are looking is whatever the next state we want, that is the D input basically. Let's work on the flip-flop 1 first. Flip-flop 1, X is 0 case, let's look first. So based on X is 0 case, it is the present state. And with X is 0, this is coming to be the next state. So to switch from this present state to the next state, what D input we need to apply with X is 0. 0 to 0, to get the 0, D input must be 0. This let us name D1. And 0 to 0, again 0. 1 to 0, again 0. And if you come to the X equal to 1 case, so if you come to the X equal to 1 case, present state is same this, but the next state here, it is the next state. It is the next state. It is with X is 1. So 0 to 1, it is 1. 0 to 1, it is 1. 1 to 1, it is 1. So this is the flip-flop 1 input. Similarly, let us look to the flip-flop 0. With X is 0, with X is 1. D0. This is the present state. Next state with x is 0 is this. So 0 to 1, 1, 1 to 0, 0, 0 to 0, 0. And next state with x is 1 is this. So 0 to 0, 0, 1 to 0, 0, 0 to 0, 0. So this combined table now we are naming state transition and excitation table. State transition and excitation table. So we are using the D flip-flop so that we are using the D flip-flop excitation table. If at all we want to use the JK flip-flops, we are supposed to use the JK flip-flop excitations. If you want to use say T flip-flops, we must use the T flip-flop excitations. So work is coming to be same irrespective of the flip-flop which we want to use. The corresponding flip-flop excitations we need to use. Now from this state transition and excitation table, we must read the equations for flip-flop inputs. If you look to the D1, flip-flop 1 input is a function of x, q1, q0. So if at all you are looking at the minterms, x is 0, of course no minterms. With x is 1, we are looking 3 minterms. So x is 1, x, q1, q0, it's the one we are following. So x is 1 and q1, q0, if you read, it is 0, 0. It is one minterm. The minterm is 4. Next we are looking x is 1 and q1, q0, 0, 1. So minterm 5. Next x is 1, q1, q0, 1, 0. It's a minterm 6. So we are looking to the minterms as 4, 5 and 6. And we are looking here. We are not having the usage of x is 0, q1, q0, 1, 1. This we are not using. And similarly, we are not using x is 1, q1, q0, 1, 1. So this becomes the don't care. So don't cares we are looking as 3 and 7. So these are the common don't cares in both these flip-flop inputs. Similarly, if you look to the D0, D0 also is a function of this x, q1, q0. The minterms, if at all we are looking, the minterms we are looking only one combination. That is x is 0, q1, q0, 0, 0, minterm 0. And don't cares 3 and 7. So these are the compact canonical SOP expressions for the flip-flop inputs. Now, by using K-maps, we need to read the minimal forms. So if we try for the minimal form for D1, four, 5, 6, 7, 4, 5, 6, 7 becomes a 4-cell subtube. So it becomes x, and coming to the D0, 0 is a minterm. So it is independent cell, hence it is coming to be x complement, q1 complement, q0. It is a expression for D0. Now these inputs are to be implemented at the respective flip-flops. It is the implementation for this finite state machine using D flip-flops. Hence it is the answer to the C bit. It is the answer to the C bit. So let's look to the next question. The finite state machine described by the following state diagram with A as starting state. When an arc labeled is x by y, x stands for 1-bit input and y stands for 2-bit output. This is a state diagram which is given as per the question. The question is, what is the operation of the circuit? So for that we are having some options. One option we are looking, Output is the sum of the present and previous bits of the input. One option we are looking outputs 0, 1 whenever the input sequence contains 1, 1. Outputs 0, 0 whenever the input sequence is 1, 0. And D option given none of the above. So you can see here, we are looking, there are 3 states in the finite state machine. When circuit is in the A state, if X is 0, we are looking, it is in the same state with output 0, 0. But as and when X is 1, it is coming to B state with output 0, 1. When it is the B state, with X is 0, it is coming to A state with output 0, 1. But as and when X is 1, it is coming to C state, the output is 1, 0. Whereas here it is 0, 1, here it is coming to be 1, 0. And when it is a C state, with X is 0, it is coming to A state with output 0, 1. With X is 1, it is coming to 1, 0. It is giving output 1, 0, and of course in the same state C. So you can see here, initial state is mentioned as A, that is starting state. When it is the initial state, it is not received any bit, it indicates. Whenever it is getting 0, of course it is the same state, but as and when X is getting 1, it is coming to B. The output is 0, 1. When it is a B state, if at all it is getting 1, it is coming to C state, output is 1, 0. So you can look, present input is 1, the previous input is 1, 1 plus 1 becomes 1, 0. It is coming to C state. So it is output. But whenever it is getting 0, the sum, if at all you are looking, it is 0, 1, whereas 1, 1, sum is 1, 0, but here it is 0, 1. So we are looking, it is 0, 1, and of course it is coming to A state. And similarly, whenever it is in a C state, if at all it is getting 1, present state 1, previous 1, 1 plus 1. So we are looking to the output, sum of the present and previous as 1, 0. But if at all it is getting 0, present state is 0, previous is 1. So 0 plus 1, it is giving 0, 1. So based on this, what we are able to understand is, it outputs the sum of the present and previous bits of the input. Hence, answer is option A. It is giving always the sum of the present and previous bits. Whenever we are looking to the 1, 0, sum of the present and previous, if we are looking 1 plus 1, 1, 0. But if at all it is getting 0, present and previous, if at all we are adding 0 plus 1 is 0, 1. If you check like this, so it is giving basically the sum of the present and previous input bits. Hence, answer is option A. Option A is the answer. So let us go to the next question. It is also the question in the GATE exam 2001. The question is, a sequential circuit takes an input stream of zeros and ones and produces an output stream of zeros and ones. Initially, it repeats the input on its output until 2 consecutive zeros are encountered on the input. From then onwards, it produces an output stream which is the bitwise complement of the input stream until it encounters 2 consecutive ones, whereupon the process repeats. The question is, we have to give the state diagram for this. So, how it is working, you can see, suppose we are having input bit stream X, as it is mentioned is a combination of zeros and ones. So it is giving a combination of zeros and ones, something like this. So whenever we are having the circuit with the input of this bit stream, based on the description you can see, initially it repeats the input and its output until 2 consecutive zeros are encountered. So that the circuit is producing output as it is until it is not encountering, it is not receiving two consecutive zeros in the input bit stream X. As long as it is not getting two consecutive bits as 0, until to that it is producing output as it is to the input. So you can see the output, if at all I am naming the output as Z, Z will be as it is until it is not receiving two consecutive zeros. So here we are looking two consecutive zeros it encountered. So once it is encountering two consecutive zeros, it is mentioned from then onwards it produces an output stream which is a bitwise complement to the input. So then onwards, once it is encountering two consecutive bits are 0, it is producing bitwise complement to the input. How long it is producing bitwise complement? Until it encounters two consecutive bits are to be 1. So until it is not receiving two consecutive bits as 1, it is going to produce the bitwise complement. So we are looking at the place, at the time we are looking to consecutive bits are 1. Until to this it is giving the bitwise complement. Then after it repeats. So then after its check will be now two consecutive bits are to be zeros. So that then after it is producing output as it is to the input until it is not encountering two consecutive bits or zeros. Hence, if at all it is the input bit stream X, we are looking to the expected output from the circuit supposed to be this. So it is the operation we want from this state machine. So you can see here the functionality of the circuit is as simple as something like this. It is getting the input bit stream X. Whenever it is getting the input bit stream X, it is working based on the input bit stream. Either it may be producing output as it is the input or it is giving the output complement to the input. So in a simple way, if you want to understand, it is working either maybe as a buffer or it may be working either maybe as a NOT gate, as a inverter. But when it is to work as a buffer, when it is to work as an inverter, it has to do with the intelligence. Once it has to do intelligence means the intelligence is possible for any living thing or non-living thing. The intelligence is possible if and only if there is some memory. So it has to produce either maybe the bit as is of the input or maybe producing output complement to the input. It means it is working either maybe as a buffer or maybe as a NOT gate. So this operation it has to do with the intelligence. So once it is to do with the intelligence means it required or it need to have some memory. Once we are talking it need to have the memory, then we need to use the flip-flops. Once we are using the flip-flops, the circuit becomes a finite state machine. Okay, for a finite state machine, the description what we are having for the operational circuit is to be represented, possible to represent with the state diagram. Of course, it is a question what we are looking. So if you tell we are looking to the solution now, the state diagram we are trying as per the question. Suppose if you take state of the circuit is S0, it is the present state of the circuit. So when it is in the present state of S0, as long as it is not getting 0, no need to bother. But as and when it is getting 0, it is to get alert because it is checking two consecutive bits are to be 0 in the beginning. So as long as it is not getting 0 means equivalently we can talk as long as it is getting 1, it is in the same state with output same as the input. As and when it is getting 0, it is coming to the next state, let us name S1, and output must be same as the input. It means if the circuit is coming to the state S1 means it is possible if and only it is getting 0. When it is S1 state, there is a possibility the incoming bit may be coming to be 0, the incoming bit may be coming to be 1. If at all incoming bit is coming to be 0, then what it is looking to consecutive bits are to be 0, it is encountered. So then onwards its operation is totally different. Hence it must switch to a new state. Let us name the new state as S2. So it is coming to S2 state from S1 as and when it is getting 0 and output must be same as the input. But if at all it is getting 1, it is what it is looking to consecutive bits are to be 0, it is unable to get. So if at all it is getting 1, it is coming to S0 state, output same as the input. Giving the output same as the input, it is coming to S0 state. So circuit is in the S2 state means it is already received 0, 0. Then only it is possible. Otherwise it is not possible. But all it is in the S2 means it has to get 0, 0. Then only it is possible. And once it is S2 state, then we know it is to bother for 2 consecutive bits are to be 1. So it is to be get alert for 2 consecutive. It is to get alert whenever it is getting 1. When it is S2 state, no need to bother if at all it is getting 0. It is to get alert if at all it is getting 1. Based on this, we can speak. As long as it is not getting 1, as long as it is not getting 1 means as long as it is getting 0, it will be the same state S2, output will be complement of the input. But as and when it is getting 1, it is to alert. So it is coming to S3 state, and of course output will be complement of the input. It means whenever it is in the S3 means it is already received a bit as a 1. So when it is S3, the next bit may be coming to be 0, the next bit may be coming to be 1. If at all the next bit is coming to be 0, if at all the next bit is coming to be 0, when it is S2 state, it means it is received already 2 bits are 0, 0. When it is S2 state, it is to get alert. It is to get alert. For 2, it is to give the output complement to the input, and it is to get alert whenever a bit is getting as a 1. Because as and when it is getting 2 consecutive bits are 1, it is to switch to the initial state as per the question. Hence, whenever the circuit is in S2 state, it is to get alert if at all it is getting a bit as a 1. In other way, as long as it is not getting 1, it means as long as it is getting 0, it will be in the same state and output complement of the input. But as and when it is getting 1, it is coming to a new state S3, because it is expecting the next bit may also coming to be 1, and of course output complement of the input. When it is in the S3 state, it means it is already received a bit as a 1, and the next bit may be coming to be 0, or the next bit may be coming to be 1. If at all the next bit is 0, what it is looking to consecutive bits are to be 1, it is not getting, so that it is coming to S2 state with output complement of the input. But if at all it is getting 1, if at all it is getting 1, what it is looking, it is trying to track 2 consecutive bits are 1, it is received, so that it is coming to the initial state S0 with output complement of the input. So that it is the state diagram for this finite state machine. So we are looking, there are 4 states. Once we are having 4 states, if you want to go further, work will be implementation. So we need to use the 2 flip-flops. So to distinguish 4 states, we need 2 variables. 2 variables means each variable is to be stored 1 flip-flop. Hence we need the 2 flip-flops. And we need to make the proper assignment. After state assignment, we have to develop the state transition table. Later, whatever the flip-flops we want to use with that excitation table, from the excitation table, as similar to the previous question, we need to work for the flip-flop input equations. So with those flip-flop input equations, we can implement the circuit. So the more necessary thing for this question is developing the state diagram. That is the most important thing. The latter work is coming to be, it is just paperwork similar to the first problem what we did. It is also a question in the 2005 GATE exam. It is mentioned, the following state of the following diagram represents a finite state machine which takes an input a binary number from the least significant bit. Which one of the following is true about this finite state machine? So one option is given, it produces the output as it is of the input bit binary number. And B option is mentioned, it computes 1's complement of the input binary number. C option is mentioned, it computes 2's complement of the input binary number. And D is mentioned, none of the above. So we need to recognize what is the operation of this finite state machine. The best way, simple way to check the operation is, let us take some input bit stream and let us check what we are reading as the output based on the finite state machine. Suppose we are having a input binary number from LSB, it's look like this: 0, 0, 1, 0, 1, 0, 1, 0. It is the LSB bit. So it is taking, the circuit is taking the LSB bit first. So based on that, let's check what we are going to read as the output. When initial state it is Q0, if it is getting 0, it's same state, it is in the same state, the output is 0. So next bit 0, so same output. If at all it is getting 1, it is giving the output same as the input and coming to Q1. When is the Q1 state? If it is getting 0, it is giving 1. If at all it is getting 1, it is giving 0. So basically it is providing complement operation when it is the Q1. So it is the output what we are reading. So based on this, you can see it is not producing the output same as the input. So option A is not correct. It is mentioned option A, it produces the output as it is of the input binary number, of course not coming. And option B is mentioned, it computes the ones complement of the input. And if you check, is the ones complement of the input? No, it is not the ones complement of the input. So that it is also not correct. Coming to C, it computes 2's complement of the input binary number. And of course you can check, this is the given binary number. And if you want to read the 2's complement, let us read first 1's complement. 1's complement is this. So plus 1 is a 2's complement. So we are looking here 0, 0, 1, 1, 0, 1, 0, 1. So you are looking, it is a matching. Hence, circuit is producing the 2's complement of the input. So the answer is option C. Answer is option C. This type of questions we'll be having in the finite state machine in the GATE exam or maybe in the IES exam. This type of question generally we'll be having as the questions.